So, good morning, everyone. So today we are going to finish this relational data model. So today we are going to kind of more focus on the normal forms. So I think in the last class we kind of discussed at the end of the class, we kind of discussed some concepts. One is the super key and the key. So I think super key and the key, we have been discussing them for quite a while, I think in a couple of lessons. And for the prime attribute, that's basically the new that's the new concept. I'm sorry, my machine is a little bit slow for some reason. Okay, so it's kind of a new concept. So a prime attribute basically is an attribute that appear in at least one key. Okay, so key here basically we talking about the candidate keys. So candidate keys basically contain both primary key and secondary key. And if an attribute appears in at least one of the keys, then that attribute is the prime attribute. So if a key has a single attribute, then that attribute is the prime attribute. If a key has multiple attributes, then each attribute is a prime attribute. Then for the non-prime attribute, basically those are the attributes that do not appear in any keys. Okay. Then I think in this slide shows example. So assume we have a student schema, and both SSN and T number are the keys. So we have two keys. Then obviously the prime attributes will be SSN and T number. Then the F name, L name, address will be the non-prime attributes because they don't appear in any of those keys. Then let's go to the fourth normal form. So fourth normal form is kind of requirement for the relational data model. So if you are building a relational database, theoretically you have to satisfy the first normal form. And the first normal forms requires that every single attribute in the relation schema must take atomic value. By atomic, it means that that attribute for every single record must have a single non-divisible values. So in other words, composite attributes, multi-valued attribute, or nested relations, those attributes will not satisfy the atomic values. Okay? By composite attribute, that usually means that an attribute has several components. For example, in a database design, when we record a person's name, so there may be at least two ways we can record a person's name. One is that we use name as attribute, and then within that name, we have three components: first name, last name, and the middle initial. Okay, so in this case, the name attribute is considered as composite. The second option is that we're going to use a single attribute for each component of the name. So we have first name attribute, we have last name attribute, and also we have middle initial attribute. Okay, so these are two separate design when people design a database for recording, for example, people's name, a person's name. Okay, so we can either treat a name as a composite attribute, means that we use a single attribute, but that attribute value will be composed several fields, subfields or subcomponents, or we use several independent attributes. I mean, one for each component of the name. So basically, in the first normal form, it requires that if you do have attribute that can be split into multiple components, in order to satisfy the first normal form, you have to create an attribute for each component. So then you satisfy that each attribute will have atomic values. And let's see some examples that the attribute is not atomic. So in the example, we have department schema, okay? And if you look at the table of the department, you can tell that the location, that attribute, is not atomic, because for some records, the location can have multiple values, okay? So in this case, the locations is considered as multi-valued attribute, okay? So then it does not satisfy the first normal form definition. So first normal form requires that every single attribute can take only one value, one non-divisible value for each record in the table. So I think the D name, D number, and MGR assistant, those three attributes can be considered as atomic attributes. But the D location is not. It is actually multi-valued. Okay. So in this case, the department is not in first normal form or does not satisfy first normal form requirements. So usually we call the first normal form as 1NF. Okay, so in this case, this department schema is not in 1NF because it does have multi-value attribute. However, if we design department in the second option, so in the second option, if you compare B and C, both relation schema has the same set of attributes, but the primary key definition is different. So department, the B in the table, in the figure B, department has a single attribute as the primary key, the D number. So primary key contains only a single attribute. But in the figure C, department actually has a composite attribute, so D number and D location, okay? So because we add D location to the primary key, then at this time we can pretty much more like change the D location from a multi-valued attribute into an atomic attribute, okay? So now if you compare these two tables, pretty much the second option pretty much make a one record for every location of a department. If a department has multiple locations, then this table will have multiple records. So after this kind of treatment, then the second department table is considered in 1NF. Okay, so that's why I want you to be sure that. So not in 1NF. Okay, so the fourth department, sorry. Apparently it does not allow me. Let me go here. No, I think, yeah. So this department is not in 1F, but the second one is in 1F. Okay, so the second department table or schema satisfies 1NF definition. So 1F simply just require that every attribute must have atomic values. So this gave another example. In this case, one is more like in this EMP PROJ, it has a nested relation under the PROJ. Okay, so what does that mean? If you look at the table, we can tell that for the first kind of a part of this table, the SSN ename, they're considered more like only has a single value for each record for that, according to the table we're showing here. So SSN and ename had a single value for each record, but P number and hours actually has multiple kind of records for a single record in this table. So it's more like this small table nested in the record. So this is called a nested relation. So if you have a table has nested relation, that means that this table is not in 1F. So the EMP PROJ underscore PROJ is not in 1F. And in order to convert it to the 1F relation, then we can do we call the normalization process, means that we're going to split or decompose this relation EMP underscore PROJ into, in this case, two smaller relation or two separate relation. Then each one of them is in 1F. So what we do is that we create one table only contains SSN and E name. Then we create a second table contains SSN, pin number, and hours. And for the second table, SSN and the pin number together is the primary key. Okay, so then it will ensure that if an employee works on multiple projects, then that employee will have multiple records in this EMP underscore PROJ2 table, and each record will show in the hours for a specific pin number. Okay, for example, if employee John Smith works on 3 different projects, and then he will have 3 records in this table, one for each project, and also recording the hours for each project. Okay. So once again, we just finished the definition of what is forced normal form or 1NF. So 1NF only requires the property of attributes. It requires that attributes must have atomic value. So 1NF does not allow composite attribute, multi-valued attribute, and nested relation. I think in the 2 examples, we do see the first one, the multi-valued attribute. The second example, we see the nested relation. Okay, now we go to this another concept about full functional dependency versus partial functional dependency. So let's first discuss kind of the definition. So assume the full functional dependency given X determines Y. If this functional dependency is considered as full, that means that Y will be dependent on the whole X or the entire X. Okay, this whole X means that if we, for example, if X contains multiple attributes, then we, if we remove one or some attributes from X, then the remaining attributes will no longer be able to determine Y's value. So in other words, all attributes in X are needed in order to determine Y's value. So that's called full. Okay. So here give you one example, like SSN pin number determines hours. So in this is considered full functional dependency in terms that in order to identify the hours for a specific project of an employee, we have to know the employee's SSN, project number together, then we are able to determine the corresponding hours for that project given an employee. So in this case, this functional dependency is considered as full, means that hours is dependent on the entire determinant SSN and P number. Okay, so this is called the full. Okay, so I think I revised this slide. Means the full, full functional dependency means that given X determines Y, Y is dependent on the entire X or the whole X. Okay, and also by default. So if X is a single attribute, then the X determines Y will be full functional dependency. Okay, because we cannot further split X, make a part of X. So X cannot be splitted further. So that's why if X is a single attribute, then X determines Y will be considered as a full functional dependency. So this full and partial solely used to examine the structure of the determinant to see if the dependent is dependent or the dependent is determined by the whole left-hand side called determinant, or the dependent only kind of dependent on the partial determinant. So based on this kind of relationship, we can tell whether a relation schema or whether a functional dependency is full or partial. Okay, so let's take some example, I think. So this shows kind of, in this slide, it shows the definition of the partial functional dependency. So given functional dependency, X determines Y, and if X determines Y is partial, then some attributes of X can be removed from X, and then the remaining attributes of X. So we have X minus A means remaining attributes of X after removing the A attributes, then the remaining attributes still can be used to determine the this. Sorry, I think Y's value. I'm sorry. So we only focus on X and determines Y. Okay. So then the partial, in this case, partial means that Y given X determines Y. Actually, Y only dependent on the partial X, not the whole X. So partial X is the root cause that Y is rely on, not the whole X. So that's called a partial, okay? And here give you one example, like SSN F name determines DNO. So means that this is a functional dependency. We have multiple attributes on the left. So since SSN determines DNO is a valid functional dependency. So I think the semantics behind SSN determines DNO basically we kind of use the table that we assume. Yeah, I'm sorry. So we have SSN determines the D number. Okay. So then I'm sorry, I forgot the. Yeah, should be somewhere here. Yeah. So since SSN is the key for that table contains SSN, F name, and DNO. So it means that SSN, given the SSN value, we are able to retrieve only one record from that table because SSN is the primary key. Then we know the corresponding D number. So in other words, we really do not need to know the F name. And as long as we know the SSN, we are able to get DNO's value. So that's why the removing F name, then SSN determines DNO still holds. If this is true, then we consider this original functional dependency is partial. By partial, it means that DNO only dependent on the part of the left-hand side attributes, not the whole set of attributes on the left-hand side. Okay, so that's partial. I want you to understand the partial and full. Okay, so by default, if a functional dependency has only a single attribute on the left-hand side, which we call the determinant. So if a functional dependency has a single attribute in the determinant, then that functional dependency will be always full functional dependency because we no longer be able to get the part of that single attribute. Okay. And that's kind of I think this gave you some examples. So let's move on to the normal form, second normal form definition. So relation schema R is in second normal form, also called 2NF, if the R is in 1F. So means that every single attribute of R must be atomic attribute. Then the second condition is that every non-prime attribute A in R is fully functional dependent on each key of R. So this basically means that every non-prime attribute must be dependent on the whole key. Okay, if that is true, then the relation schema is in 2NF. So you can tell that 2NF has more conditions than the 1F. So the 2NF is stricter than the 1F. And then later we're going to study 3NF or third normal form. And the condition on the third normal form is also much stricter than the second normal form. Okay, but anyway, if a relation schema is in second normal form, it must be in the first normal form first. So based on this definition, we can tell that if a non-prime attribute depends on a part of the candidate key, then that considered as partial dependency. Okay, so means that the key is dependent on the partial key. So the attribute is dependent on the partial key. So that's why it's called partial dependency. So 2NF does not allow partial dependency. So if a non-prime attribute depends on the entire candidate key, then it's full dependency. So now we know the partial dependency, so which means that attributes only dependent on the partial key, not the whole key. Then we also define a full functional dependency. That means that an attribute is dependent on the whole key. So in essence, the second normal form does not allow partial functional dependency, okay? Because later we're going to examine that partial functional dependency is one of the root cause for the redundant data in a table, okay? So let's see the example here. So assume we have a relation schema, EMP underscore PROJ, okay? So it has SSN project number, ename, P location, hours, and a DNAM. So SSN and the project number are underlined. So that means that the two together is the primary key. Okay, now we have a set of functional dependency that defined on the attributes of this relation. So we have SSN determines ename, project number determines pname, project number determines P location, project number determines DNAM, and last one, SSN project number determines hours. So we have 5 functional dependency. But if you look at these 3, okay, so these 3 actually are special because they all share the determinant, so the left-hand side attributes, okay, the attributes on the left. So then we can merge these 2 because they all share the determinant. We simply just merge their dependent together. So it means that we can replace these 3 separate functional dependency with this single functional dependency. So these 2 are equivalent. Okay, you either want to split them into 3 smaller functional dependencies that share the determinant, or you can just combine these 3 into a single. Okay. Then the question that asks, so if we assume that every attribute is atomic, okay? So assume each attribute is atomic. So that means that each attribute cannot have multi-values, cannot have composite values, cannot have a nested query. So let me see if I'm able to. Okay. So if we assume each attribute is atomic, then how do we know if this relation schema in the second normal form or not? Because if we assume each attribute is atomic, that means that this relation EMP underscore PROJ is first normal form. Then we are ready to examine if it is in the second normal form. So recall that second normal form requires that every non-prime attribute is fully dependent on the whole key, okay, or depend. So that's kind of requirement for the second normal form. So let me make a copy of this one and then let's discuss. So before we're able to answer this question, okay, so we know that all attributes are atomic, okay? So I think it's basically how do we know if it is in 2NF or not? So if every non-prime attribute is fully dependent on the primary key, then it is this schema is in second normal form. If there are some non-prime attributes that's only dependent on the partial key, not the whole key. Partial means part of the key. Then this relation schema is not in 2NF, okay? So then before we're able to answer the questions, we probably have to do the, what is the prime attributes, non-prime attributes, I think, but somehow my computer's, or maybe the display is slow. So what is prime attributes? So if you know the keys, then you for sure know the prime attributes. So prime attributes basically are those attributes that appear in the key. So our key contains two attributes, then both attributes will be the prime attributes. So that's basically the easy way to identify the prime attributes. So in this example, we only have a single key. So SSM project number is the only key of this relation. But for some relation, if we have multiple keys, then we just simply list the attributes of all the keys. And then those attributes together, each one of them is called a prime attribute. Once we know the prime attributes, then we can easily find the non-prime attributes. So basically the attributes are not the prime attributes. So we have ename, pname, plocation, hours, and denom. Okay. Now we're going to examine if every single non-prime attribute is dependent on the whole key or not. So then we can evaluate those functional dependency to see if they are the full functional dependency in terms of the primary key or partial functional dependency in terms of primary key, okay? So now let's look at the first one. So we have SSN determines ename. So this functional dependency tells that ename as, sorry, it's not F. So ename as the non-prime attribute is dependent on the SSN. Then the question will be, is SSN a whole key or not? Apparently, SSN is not a whole key because the whole key is denoted here. It is SSN and project number together. So in this case, SSN is part of the whole key. Okay. So then this functional dependency will be considered as partial. Because ename as the non-prime attribute that only dependent on the partial key, not the whole key. Your whole key should be two attributes. Okay, so this is partial. So similarly, the following three, so pname, plocation, and the denom, they all dependent on the project number. So you can refer either these three functional dependency, or you can just refer this one. So this one and these three are the same. So this one indicate denom, plocation, pname as the non-prime attributes. They are only dependent on the project number. So which is not the whole key, but the partial key. So by partial key, it means that project number is part of the key, but not the whole key. So that means that those three are also partial. Okay, so last one. I think, sorry, I cannot, let's break the line. So maybe I just use P, okay? Means partial. So this P parenthesis means partial FD. Then the last one, hours. So we have hours determines, is dependent on the access and the product number together. So hours is non-prime attribute. So this functional dependency shows that hours is dependent on the entire key, the whole key. So this will be considered as full functional dependency. So here, both partial and full, the discussion of those functional dependency are actually use the primary key. So in terms of the primary key, whether a non-prime attribute is dependent on the whole key or partial key, okay? So now we probably able to understand if this is in 2F. The answer will be no. Why? Because we do have partial functional dependency. Because now some non-prime attribute, or because of partial FDs exist on the schema. Okay, relation schema, okay? So as long as a relation schema has partial functional dependency, then that relation schema is not forced normal form. I just kiss me, I don't know. Hello?
Test. This is a test of the UA little.
Okay. Because I got a call from Yola, I just want to make sure I didn't miss any important message. So, okay, good. So according to our discussion, since there are some functional dependencies are partial in terms of the primary key, then this relation schema is not in 2F. So the highest normal form this relation schema will be in is 1F, based on the assumption that each attribute is atomic. Okay? Questions? Now let's discuss the transitive functional dependency. So a functional dependency X determines Z is transitive if it can be derived from two separate functional dependency. X determines Y and Y determines Z. So what does transitive functional dependency means? That's actually define an indirect relationship or dependency between two sets of attributes. So in this example, the X determines Z actually derived from X determines Y and Y determines Z. So X determines Y means that Y is dependent on X. And the Y determines Z means Z is dependent on the Y. So through these two functional dependency, we can tell that X determines Z. So it means that X determines Z through the Y. Okay, so Y is more like the middleman. So it's related to the X and also relates to the Z. Then we have X determines Z as a transitive functional dependency. By transitive, it means that Z is not directly determined by X, rather is indirectly determined by X because through this middleman Y. Okay. So here, let's see some examples. So assume we have a relation schema EMP. So SSN is the primary key. It also has ename, dnumber, and mgr SSN. So if we assume that SSN determines dnumber, so that's considered as a default functional dependency because SSN is the primary key of this relation schema. So a primary key always determined all other attributes in the relation. So in other words, we can have SSN determines ename, SSN determines dnumber, SSN determines dmgr SSN, or we have a single functional dependency like SSN determines ename, dnumber, and mgr SSN. Okay. So since SSN determines dnumber and dnumber determines dmgr SSN, so that's kind of a more like a intrinsic relationship between the dnumber and the dmgr SSN. So this kind of a relationship is very intuitive. So it means that if we know a department number, then we're supposed to be able to get which department that dnumber refers to. Then we're supposed to be able to get the physical department information, including its manager's SSN. Okay. So now we have two functional dependency. SSN determines dnumber is the default, and the dnumber determines dmgr SSN actually is kind of a relationship between these two attributes. Then we can consider SSN determines dmgr SSN. So this is as transitive. So by transitive, it means that a non-prime attribute is transitively dependent on the key. So SSN is a key. Okay. So transitive functional dependency in terms of the primary key is not considered good. Okay. So that's called a transitive. Okay. But later we're going to study the, I think, more easy to understand definition for the transitive functional dependency. Now let's study the third normal form. So we know that the second normal form does not allow the partial functional dependency in terms of the primary key. Okay. Then the third normal form, if a relation schema is in third normal form, it must be in 2NF first. Okay. Then the no non-prime attribute A in the relation is transitively dependent on the candidate key. Okay, so this condition is very important. So it means that no non-prime attribute is transitively dependent on a candidate key or the primary key, either way. So this second condition can be easily translated as no non-prime attribute is dependent on another non-prime attribute. Okay, so if we don't have any functional dependency, that shows that a non-prime attribute dependent on another non-prime attribute, then our relation schema can be in third normal form. If we do see a functional dependency that both sides of that dependency have only non-prime attributes, or both sides are non-prime attributes, then that functional dependency is considered as transitive. Okay, the rim, because I think the reason is very clear. If we have A determines B, so if both A and B are non-prime attributes, okay, if K is a key, or maybe is a candidate key, okay, then by default, the default functional dependency means that every key will determine all the other attributes. So then by default we have K determines A. Okay, so now we have K determines A. K is a key of the relation. Then A determines B. Then we have this K determines B as transitive. So that's the why if we have functional dependency that both sides of that functional dependency are the non-prime attributes, then this is considered transitive, because by default we know that a key is is determining all other attributes in the relation. So we have key determines A, then so we have K determines A determines B, that's the then things. K determines A, that's the default functional dependency. So that's default. Then A determines B, that's the given. Then we have K determines B is transitive. So it means that attribute B is transitively dependent on the primary key. Okay, so that's not considered good. So in essence, so if you see a functional dependency, if both sides are non-prime attributes, then that's considered a bad sign of your database design. It's not good. So because that indicates transitive functional dependency. Okay. Okay, so I want to skip this one. If you're interested, you can discuss. You can read that one. So now for the normalization to string F. So why do we need normalize relation schema into string F? I think the main reason is that we want our data does not contain the redundant data, and also we want our data to be consistent over time, regardless how data change. So that's why the 3NF really, if a relation schema satisfies 3NF, it really preserves some good properties that able to maintain the data consistent over time, and also it does not have redundant data stored in the database. So for the normalization process, it only used to or apply to the relation schema that's not in 3NF. Okay, if a relation schema is not in 3NF, then we can utilize its functional dependency to perform normalization process. So this normalization process is very simple. So it only takes 2 steps. So first step, for each partial or transitive functional dependency, we create a relation that includes all attributes of that functional dependency. So the step 1 we may repeat multiple times until we finish creating a relation schema for every partial or transitive functional dependency. Okay, then we move on to the step 2. So then the step 2, we're going to create a relation that contains the primary key of the original relation, as well as all non-prime attributes that are fully dependent on the primary key. So step 2, we only perform one time, but step 1 we may repeat multiple times. For example, if a relation schema has, for example, 2 partial functional dependency, then we have to run step 1 twice. If a relation schema in total has 3 partial or transitive functional dependency, then we have to run this 3 times, one for each partial or transitive functional dependency. After we finish step 1, then we move on to the step 2. Now work on that, okay? So let's see the example here. I think this is a very good example in the sense that given relation schema here, okay, and it has one attribute as the primary key, so property ed, okay. Then if you look at the functional dependency, we actually have 2 keys. So one is a property ID, because this functional dependency shows, let me see if I'm able to. So the FD1 basically shows that property ID number determines county name, lot number, area, price, and the tax rate. Okay, so this is the first functional dependency. Okay, then FD2 shows that county name lot number determines property ID number, area, price, tax rate. And FD3 indicate county name, my screen display, the response time is pretty slow. So county name determines tax rate, and FD4 shows area dependent price. Okay, so you may ask, how can I interpret those kind of notations? So this is more like a foreign key and a reference key. So for functional dependency, they either made of the bar points to a bar, under an attribute, or the arrows points to an attribute, and all those bar and arrows will be connected by this horizontal line. So that means that attribute, pointed by the bar should be the determinant. So that's why for the FD1, only property ID is pointed, by the bar. So that means this is the determinant. Then all the remaining attributes are pointed by the arrows. So that means those are the dependent. Similarly for the FD2, so county name and the lot number, they are all pointed by this bar, okay, not the arrows. Then the property ID, area, price, and the tax rate, they all pointed by the arrows. So that means that these two attributes pointed by the bar should be put on the left as determinant. So we have county name, lot number. Then the remaining attributes pointed by the arrows should put into the on the right side of these functional dependencies, because they are the dependent. Okay, the FD3 is the same thing. So we have county name pointed by the bar, so we put on the left, and tax rate put on the right. And the last one we put area pointed by the bar on the left, and the price on the right. Okay, now actually if you pay attention to the FD2, okay, so this FD2, basically this functional dependency contains all attributes of the relation schema. And so in this case, we consider county name, lot number is another key, because it determines all other attributes in the relation schema: property ID, area, price, and tax rate. So that really indicates this relation schema has two keys. Okay, so one is based on FD1, FD2, we can tell that county, I'm not able to type because this, okay, they become county name, lot number together is a key. So in this case, should be the candidate key, okay, or the secondary key. Okay, so now we have two keys. Property ID is one key, and the county name and lot number is another key. So now we can have the prime attribute should be the property ID number. So that's coming from the primary key first. Okay. And the second one we have from FD2, we can tell that content name and the lot number. Okay. So this basically means that we have 3 prime attributes. Then for the non-prime attributes, so for the non-prime attributes, we're going to only have area and the price and the tax rate. Okay, so we have, I think, 6 attributes in this relation schema. 3 attributes are the prime and the 3 are the non-prime. So we have prime attributes. Okay. Now we can tell that based on the prime attributes, based on the key information, we can tell that which functional dependency is full, which is partial, or which is transitive. Okay. So the first one, of course, it is full because we have primary key determines all other non-prime attributes. So it means that the remaining, content name, lot number, area, price, and the tax rate, they're fully dependent on the primary key. So this is a full. Okay. Although content name and the lots actually the prime attributes. So, but still it indicate area, price, tax rate. Those 3 non-prime attributes is dependent on the whole key. So this is a full functional dependency. The FD2 the same. Now, so FD2 basically shows that content name and the lot number determines all other attributes of the relation. So in this case, this is also full. So it means that the left-hand side, we have a whole key. So this is a candidate key. So this is a full. Sorry. Okay. Then the next one, we have a content name determines tax rate. So apparently, content name itself is not a key. So we only have a single attribute, property ID as a key. But content name is part of a candidate key. So we have content name, lot number is a candidate key. So since content name is a part of a key, not the whole key. So in this case, will be the partial. Okay, so the FD3 is partial. The last one, we have area determines price. So both area and the price, they are non-prime attributes. So in this case, this one will be the transitive. So for the transitive functional dependency, if both sides of the functional dependencies are non-prime attributes, then that functional dependency is partial. Okay, so this means the last one, area determines price, is partial functional dependency. Okay, so that's pretty much for the normalization. So if we want to normalize this functional dependency, we only need to create, because according to the procedure here, we just need to create a relation schema for each partial and for each transitive. So here we have only one partial and one transitive. That means that we're going to create one relation for the based on the FD4. Okay, so so this is how it shows, but I don't want you to so we're going to use that normalization process. Okay, so I think we can make it a little bit small. So for the normalization process, we're going to step 1. We have to follow that 2 steps. So we create a schema based on FD3, which is the partial. Okay, then we're going to create another schema based on FD4. Because that's the, okay. So that's step 1. We need to handle each partial and each transitive functional dependency. So once we finish that, then we move on to the step 2. So step 2, we're going to create a schema contains the primary key of the original schema plus all attributes that fully dependent on that. So in this case, so FD3, we're going to end up like maybe the called contain text, called the text, okay, text table. So it contains contain name and text rate. Okay, so this relation schema, the determinant will be the default primary key of this new relation. For the second one, the same thing. So this one will be the price table, for example. Price table, we have error determines based on the FD4 price. Okay, so then error is underlined. Okay, so then step 2, we need to create a schema. So we have a loss, for example. Maybe I call it loss 1, loss info. How about that? So now what we're going to include in this table. So the primary key of the original table, that will be property ID number. Okay, then how do we determine the other attributes? So we first probably cross the attributes from the original schema. So like the tax rate, because tax rate is in the text table. So tax rate, so pretty much we cross attributes that appears in the partial or transitive functional dependency on the right side. So we have tax rate, so we remove tax rate. Okay, and then the other one, what we need to remove is the price. Okay, so then all the other attributes we need to include it, okay, in the final. So we're going to have a contain name, lots, number, error. Right, so yeah, we have 1, 2, 3, 4, exactly, we have 2. So finally, what we're going to do is that we are going to use this 3 smaller relation schema to replace the original relation schema, the lots. Okay, so this is how we're going to do the normalization. So this is how we're going to do it for the normalization process. So this is a very tricky example. The reason I want to show you here, just let you know that sometimes, although the primary key of a relation schema is, always is underlined, but based on some functional dependency, we can also derive the other candidate keys, or we call the secondary keys, because those are the keys, but not designate as the primary key. Okay, so in this case, we also found out that contain the name and the lot number together is the primary key, because these 2 attributes determine all remaining attributes of the relation schema. Okay, then we're going to use the idea like the partial functional dependency and the transitive functional dependency to evaluate if there's any partial or transitive functional dependency. Apparently, we have 1 partial, 1 transitive. So this 1 partial functional dependency will prevent this loss for being in 2NF. So means that because of these 2 is partial, then loss can only be in 1NF. first normal form. It cannot be in second normal form. Okay, then we do the normalization process. So we create a relation schema for each partial, and also create relation schema for each transitive. Then we create the last one. A relation schema contains the original primary key plus any non-prime attributes or prime attributes that are fully dependent on that primary key. So we end up with this loss info. So finally, this original one big table will be replaced with these three smaller tables. Since we arrive these three smaller tables using normalization process, that means that all three tables, these three smaller tables, will be in 3NF by default. So 3NF normalization process will guarantee that the resulting relation schemas will be all in 3NF. So we're going to, I think we're going to discuss a little bit, kind of finish this part discussion in the next class. And also we're going to have some in-class exercise. Then we are pretty much done for the relational data model. So the next week, we're going to give a quick review of the entity relationship model. Then we will move on to the SQL programming. So any questions? Okay, so if you do not have any questions, then we are done for today. Thank you.